Okay, we're going to start section 2.7. I know that your previous notes end where Kyle is. We're not going to finish off those last two examples. They're word problems, and we're just going to learn a better way to do those word problems anyway. So we're just going to go here. And we're going to do something called modeling with functions. And this is where you can really see the power of mathematics at work, meaning you can apply mathematics to the real world. Now, some people will say, well, I'm never going to do a problem like this in the real world. I get that. I get that you're probably not going to be a farmer that's going to make a pen. I know that. But here's the difference, okay? Can you build a house with a hammer and nails? You need more than that, right? But just for the framing part. I mean, if you had an air nailer and you had a hammer and nails, you could do it with the hammer and nails, right? But would you rather have the air nailer? You sure would. It's a lot more efficient. It's a lot more effective, right? It's the same way with math. You can get by in life without math. For example, the other day I was walking through Walmart. There was this guy in front of me. He owed $5.83, so he took out the 5. And I felt bad for him because he was embarrassed. He reached in his pocket, and he had a ton of change. I mean, like, the kind of change you keep in, like, little buckets. You, like, take it to the bank and, you know, see how much money you get by emptying it out. He took out the whole pile of change and set it up on the counter. And I realized what he was doing. He didn't know how to count 83 cents. He didn't know how to do it. And so the lady counted his 83 cents for him. He paid $5.83 and he put it all back in his pocket. I just felt bad because he was going to the store. He was buying what he was supposed to buy. He was taking care of his family. But he didn't know how to count change. And is he still able to make it through life? He sure is, even without that arithmetic. However, it's nicer to have a little bit more mathematics on your side. So that's what life is like. If you don't have math, sometimes it's like just using a hammer and nails to get by. But we want the power tools. And so that's why we learn how to do this. Every time I set up a word problem for you, we're going to divide it into 4 squares, just like this. You may say, I don't need to do that, Mr. Gens. Fine, don't do it. But then read my research, because last year, this is one of the techniques I used. Okay, graphic organizers. This is a graphic organizer used to help you organize your work. Their impact on higher level secondary mathematics, the kids who did this on their tests scored significantly higher than kids who didn't. And if you don't want to do it, that's fine. I'm not going to make you. But if you don't get how to do a problem, the first thing I'm going to have you do, draw 4 boxes. First thing we do is we model, then we write a formula, and then we write a function. Sorry, I'd rather use this notation. And then we solve. And the problem is this. Farmer is making a pen out of 480 yards of fence. So he's got this rectangular pen. Okay, he's going to divide it into 3 equal sections. So we'll make those as equal as possible. The goal of this farmer is to maximize the area. See, if he can maximize the area, that way his sheep, or whatever he's having in there, are going to have more room to run around. They're also going to have more grass to eat. He's going to maximize his efficiency if he finds the maximum area. Well, what is the equation for area? Length times width, base times height. We'll use these two. Just, you need 2 variables for area. Let's go back over to my drawing. What would you label this? L or W? W. And so all of these would represent a W. The top and bottom would represent L. Now there's a restriction to how big we can make this fence. We only have 480 yards of fencing to use, which is a lot. I mean that's like 1.5 times, on a football field. But so you tell me this. What's an equation that would relate these L's and W's to our 480 yards of fencing? Very good. If we add up all the W's and we add up all the L's, that's going to add up to the 480 yards of fencing that we need to use. So I have 2 equations here, and I have 2 variables. What we would like to do is take this information, and we would like to write a function for the area in terms of a very specific variable. You're always used to seeing x on the inside there. We're going to name a variable that we would like to write a function for to solve this problem. So I can either solve for L or solve for W in this problem, it's going to be easier to solve for L. 2L equals 480 minus 4W. I subtract the 4W over. So what is L equal to? $240 minus 2W. What can I do with that 240 minus 2W? Yes, plug it in. Or the mathematical word we use is substitute. We will use the substitution. And I will plug it in for L. So, your new equation, will your new equation have the variable L, or will your new equation have the variable W? W. So we put a W there. And the area in terms of W is going to be equal to my length, which is 240 minus 2W times that W right there. So my area in terms of W is equal to 240W minus 2W squared. What shape is that? Parabola. Is it right side up or upside down? It's upside down. I'm going to draw it. It looks something like that. Does that parabola have a maximum or a minimum? What are we trying to find in this problem? Maximum area. Ooh. See? Isn't quadratics cool? We're able to apply them to real-world problems to be able to find maximum area. Maximum is a great idea. Again, maximizing profit, minimizing cost, stuff like that. We like that stuff. So, what variable represents my x-axis here? Is it A or is it W? If you look at this, which variable do you think goes on the x-axis, A or W? The W. That's where your x would normally be. And what variable is where the y would normally be? A for area. So the y-axis is the area, and the x-axis is the width. What is this part of the graph called? The vertex. How do you find the vertex? So if we can find the maximum point of that graph, or the vertex of that graph, we can then maximize the area. All I do is take negative b divided by 2a. What's negative b? Negative 240. What's 2 times a? So the b value is the value in front of the linear term, or w to the 1 power. Whereas the a value is the one in front of the squared term, or negative 2. Okay, so 2 times negative 2 is negative 4. And what's negative 240 divided by negative 4? Positive 60. Look at that. Now, I don't know my y value yet, do I? But let's even see if we have to figure it out. The question is, what dimensions? What dimension should he make the pen to maximize the area? Well, we figured out the width was 60. What other piece am I trying to figure out? Am I trying to figure out the area, or am I trying to figure out the length? The length. So, you could do that, or I could plug it in right here. See? Length is 240 minus 2w. So if I take that 60 and plug it in, 2 times 60 is 120, and 240 minus 120, 120. There's multiple ways to go back and find L. That's just one of them. So in order to answer the equation, we say 60, forgot how to write today, 60 yards by 120 yards. Those are the dimensions of the pen. What do you think? If you saw a problem just like this, could you do one? Maybe. Let's try another one that's very similar. I have lots of like practice word stuff where you don't work out the whole thing and just write the function. We're going to skip that because I want to get to enough to where you could at least start an assignment. So we're just going to do 2 more examples, and they'll go a little bit quicker than that last one. We're going to start with example 4. Yeah. Yes. W on the outside came from right here. 240 minus 2W is L times W. So that's the W on the outside right here. Good question. Okay, now you guys got a good introduction. You'll be able to do a lot of this problem and anticipate exactly where it goes because you're my super smart class. Problem 4, a farmer builds a fence against a barn. As soon as I see a word problem, I do this. We do word problems in calculus coming up in a month and a half, and we are going to draw the 4 boxes right away. Here was interesting. I started this in pre-calculus when I had Chrissy and Corbin and Andrew and Katie and Greta and those people in pre-calculus. When they got to calculus, I didn't even need to, they just drew the boxes right away. Not because they knew I was going to do it, but because they found it helpful. So we draw it. First thing we do, we model it. Farmer builds a fence against a barn. I've got a barn. Let's put his fence. Fence against the barn. So he only needs 3 sides of the fence, not 4. What is the farmer's goal in this problem as you read it? What's he trying to do? Maximize area. So again, that tells us that we write down an area function or an area equation. Area is equal to length times width. Let's go back over here. What do I got to label? Width, length. Got it. I only have 320 feet of fencing. Somebody give me a formula. 2W plus L equals 320. Scott's correct. Any question where I got that? Is it going to be easier to solve for L or easier to solve for W? Solve for L. L is equal to 320 minus 2W. I'm going to take that. I'm going to plug it in for L. Now I can write my function. I have a function for area in terms of what variable? W. You're right, we solved for L, but the variable that's going to be up there is W. And what is that area function going to be? Whole thing times W. Distribute the W. Krista D, did you see then where we got the W? Okay, that connected from last time. Okay, thank you. All right, so then we're going to draw our parabola. This is a parabola, right? Does it go up or down? Down. So does it have a min or a max? As a max, does that match with what we're trying to find? Because one of the problems that you're going to do in your assignment is looking for a minimum. Question. Due to the value in front of the squared. So if we were to write this in standard form, say y equals -2 w squared plus 320 w, you can tell that it has an A value of -2, a B value of 320, and a C value of 0. So it has a y-intercept of 0, and you can tell the -2 makes it go down. Does that answer your question? Good question. Should, as long as the problem works out that way, but there are strange situations, which I won't give you, where that's not always the case. So you do have to pay particular careful attention to the design of the problem. Most of the time, yes, you can look at it and say, okay, I'm maximizing, so I should see a parabola that's going down. That's what you should see. Okay, what is my x-axis label? W. What's my y-axis label? A. I do that so I know what I'm finding, what I'm solving for. So often people come up with an answer here. They're like, what did I find? Well, what spot are we trying to locate? The vertex. We find the vertex by doing -b divided by 2a. What's -b? -320. Divided by 2a, -4. -320 or -4. Positive 80. 80. What does 80 represent? The width, because you can tell, because you labeled it, because you're a good student. If I plugged 80 back into this function, what would I get? I wouldn't get 0, I would get a y value, and that y value would represent the area. If you plugged 80 back in, it would tell you the maximum area. Are you trying to find the maximum area? You're trying to find the dimensions that would maximize the area. Well, I know one of the dimensions. What do I know? The width is 80. I now need to find length. 320 minus 2 times 80, so 320 minus 160 is 160. Very good. So we can answer the question, what dimensions? 80 feet by 160 feet, which is about the size of my yard that I have all those leads in case you were wondering. Just in case you're curious. I could just have you guys all over for a big party we could rake together. We could jump in them, we could have, apple crisp afterwards. Oh, you need a pass? Leaves. Or you take this. There you go. Alright. What do you think? You okay? Do you guys understand that this problem is just slightly different from the previous one? So, that's what I'm trying to tell you guys, that, you're smart enough where I could give you the same problem design over and over again, but I know you can do every single one. So the problems that you see, they might have a small twist. And you got to think through that. If you get it wrong the first time, don't worry about it. Trust me, don't worry about it. Okay, we're going to try one more. On the next side, problem number 5. A box with an open top is to be constructed to form a rectangular piece of cardboard. At this point, I stop and I draw 4 boxes. I say this is way too confusing for me to teach to everybody how it happens in my brain, so I organize it. And I start to draw a model. I've got a rectangular piece of cardboard that measures 10 by 18. It says I'm going to cut squares from each corner and fold the sides up. So what should you draw now? Cuts on the corners. What should we call those cuts? What do they measure? Say they're x by x, okay? I'm going to cut them, and I'm going to fold it up. I want to find the largest volume that the box can have. So what is my formula? Volume. Length times width times height. Good boy. That's 4 variables. V, L, W, H. Well, let's see what we can do here. Let's start with the length. Everybody agree that this is the longest side of the box? So once I cut off X there and cut off X there, is it going to be longer than 18 or shorter than 18? Shorter. How much shorter? 2x shorter. So what's the expression for my length? 18. 18 minus 2x. You cut off an x from the top and the bottom. So it's going to be shorter by 2x. The width is this part. That's going to be shorter by 2x, so you have 10 minus 2x. Yeah, when I fold it up, the height of the box is going to be the same as the size of the square that I cut out. So the height is going to be x. Very good, very good, very good. Hey, stop that. Okay. Volume in terms of x equals, what's my height? X times my width, 10 minus 2x, times my length, 18 minus 2x. And that's where we pause. What degree is that equation going to be? First degree, second degree, third degree, fourth degree? Third degree, right? You multiply all this out, you're going to get x to the third. Do you have a formula for finding the vertex of a cubic? No, in fact, we don't even talk about the vertex of a cubic. So we can't use our algebra. We got to use our graphic calculator. And you may want to multiply this all out, but does your calculator make you multiply it all out? No, you just plug it in. So take out your calculator. So I just plug it in. X, 18 minus 2x, 10 minus 2x. I think I switched them around from what I had written down, but that doesn't matter. Multiplication is commutative. And after you got that, I'm going to press Zoom 6 for Zoom Standard. Is that going to make you angry that you don't see it? Well, let's try to be smarter than the calculator here, because the calculator can only do what you tell it to do, okay? First of all, I want you to consider this, okay? We've got this shape, all right? Look at your box, everybody, and you got to be able to think this through. What is the biggest square that you could cut out and still have some volume? Somebody said it. 5. If you cut 5 by 5 and 5 by 5, would you have anything left here for a width? You wouldn't have anything. So whatever you cut out has to be bigger than 0 but less than 5, right? So if you look at my calculator, the fact that I go over to 10, is that big enough to see the spot where I want to see? Yeah, we're fine there. But the vertical part, that's the volume. Well, let's just think about it. Let's suppose you had a box that was 10 by 10 by 10. What would the volume be? 10 by 10 by 10. 1,000. So it's quite possible that 10 might not be high enough to see the volume that we want to see. So let's change our maximum. Let's go into our window. And people are always afraid to do this. They're like, should I go up to 20? Up to 30? Just make it real big. Let's go up to 1,000. Okay. And then we can always zoom in on it later. And again, I always change my scales. Whoop. Max 1,000. I changed my scales as well because I hate all the tick marks. And now when I press graph, you can see the whole thing, right? And now you could adjust it better. You can see that it doesn't quite even go up to the second one. So if I adjust this to say like, I don't know, say negative 300 and positive 300, I'm going to get a really good graph here. Look at that. Isn't that pretty? That's my shape. Does it have a maximum? It does. We're in luck. I didn't do anything. I left it alone. Left it alone. That's your shape. And the graph can tell us where the maximum occurs. This is X, this is volume. I'm trying to find the maximum right there. We don't know how to do that without calculus. In calculus, I could teach you guys how to do that. We could do it. We don't know how to do that. So what do we have to use on our calculator? So you calculate maximum number 4. We go up to that spot. I move to the right, or I'm sorry, the left. I press enter. I move to the right. Press enter. Enter on guess. And it says 2.06. And then 168.13. What does the 2.06 mean? That means the size of the cut. The size of the cut of the squares could be 2.06. What does the 168.13 mean? That's the volume. If you were to cut off at 2.06, you get a volume of 168.3. What's the question asking for? Find the largest volume. 168.13 inches cubed. Beautiful. You like it, don't you? There's a part of you that say, I kind of like this. I like drawing the graph. Emily says, I really like the 4 boxes. It's so neat, so organized. It's really cool. So I got some problems for you to practice. And these are what I want you to do. 23 has parts A, B, and C, which is basically what we laid out. But don't do part C. For 30, don't do part B. And just mind you, 33 is kind of difficult. If you don't get it, it's okay. It's okay to not get a problem. But it's not okay to give up. If we don't get it, we've got to either A, ask for help, or B, struggle through it, or find somebody who can help us out, or come in early, or do something. And if I teach you how to do it, then just try to do it again when I haven't shown you how to do it. See if you can do them. And then you'll be good. And that's all we have for today. I hope you guys have a great weekend. You got a 3-day weekend.